again, the B field, the current is proportional to 1 over R and linear in I naught, and is tangential, right? It's given by the right hand rule. The thumb is pointing in the Z direction, and the B field is along the direction of the fingers. Okay? And when we did solve for the field to do a solenoid is actually very important for a lot of application in electronics and circuits. And the B field inside, this is also by just applying the Dirichlet equation, we find that the B field inside is given by mu naught n is the winding number, the winding of the coil per unit length, okay? And it's in the Z direction. Again, you have to satisfy the right-hand rule, right? So similar to that in a way. If your current is along the direction of your fingers, then the B field is going up. Okay? Let's see. While I remember it, I think I make a reference in passing 2 lectures ago about you can use your left-hand rule and see if you get the same answer. But of course, the answer is you do get the same answer, right? You can use the left-hand rule if you want, right? But there is a left-hand rule for Ampere's law, right? But there's also a left-hand rule for the Lorentz force, right? So the square of those 2 applications, give you the same answer, basically, right? So there is no parity concentration as far as force is concerned, right? And of course, if you apply just the left-hand rule on this, you'll get the opposite B field, right? But the force also has another right-hand rule, and what matters in the end is the force. Any question on that? And also, we did the magnetic field coming out from a sheet, right? I changed my notation a little bit because I just want to conform to Purcell. It turns out Purcell is using field coming out in the plus X direction. So the current is going out of the port like this. This is the X direction, right? And then we also solve for it. There is some subtlety that I don't want to address right now. But once you solve with the Ampere's law, you get the B field is equal to mu naught times the current density divided by 2, right? This is the equivalent or the analog of an infinite slab for electrostatic, right? Here you have a current coming out, and the B field is in the Z direction to this side, and then going downward on the other side. And again, you also use the right-hand rule, right? Always use the right-hand rule. J is coming out of the port like this, right? So the B field over here is going that way, and the B field over here is going back. Right? Always remember, this is directional, right? You could easily make a mistake by reversing the order of these 2 arrows. Right? Make sure you don't make that mistake. And I think I probably made that mistake last time in that way. Any questions so far? So these are the easy examples that we can do. Just applying symmetry and Ampere's law to get all that, right? But a lot of things that are of interest is actually finite extension, as you know, right? Finite current. Say, what if a standard textbook example is what if I have just a group of current, I know. Right? Going clockwise or counterclockwise, okay? And what is the B field everywhere, right? Another, just like electrostatic, we talk about dipole. This is not a dipole, by the way. This is a loop, right? So I'm looking at field close by to the loop. But I can also have a situation where I have current again, I naught, right? This is dimension A, right? And I'm looking at the B field R at R on the B field, where R is much greater than A, right? I think we have to look at another things of interest is if you solenoid is a finite extension, how do you calculate the fringe field? And we can do the experiment here. doing it at the end. This is perfect opportunity. Okay. Mess this up. This is your solenoid, right? So it's going in that direction, right? So here I can reverse the current one way or another, and then you'll see what happened to the magnet. So this is one possibility of a current going to the solenoid. I don't know which one is the direction. I don't want to follow the, I don't want to trace it out, but as you see, that's a magnet that you have in the center, and it's pointing along the direction of the solenoid. If you do it too long, and then I can reverse the direction, right? And you see the magnet reverse. It's kind of cool, and this is also another magnet, so I can look at fringe effect. This doesn't seem to work so well. I don't know when the guy was showing it to me, he was doing a better job. It's a lot of friction. But the idea is that you can trace the P field of this solenoid. I mean, we talk about infinite solenoid, but solenoid is always a finite extension, and you have fringe effect. And see, if let's form a loop. Right? I don't know if this makes sense to you. I guess I'm sort of helping you, believe me. So I'm cheating. But otherwise, it doesn't seem to work very well. I mean, sort of work, you see. I guess it's stronger here, see? Right? You can see that? Okay. And then if I flip it, let's look at this, right? If I flip it, I think it's too heavy. See? Flip, right? Now the flip goes like that. Okay. So there's a finite solenoid for you, and then the thing here, right? If you want to look at the thing inside the thing, see, because you can apply that, but outside, what is the field? Then we have to do a better job. But before we can do that, we have to actually go back and do some math. Right? We skipped this in chapter 2, is this concept of curl. Right? And I'm going to mention this briefly. I'm not going to track everything, but if I have a surface integral, I have a line integral, a post line integral over loop C, right? F. Okay. I can break this integral into partition, right? I can partition this. And if I consider segments like this, that's called this the I segment, this is the J segment, right? If I draw it here again, then I can consider a differential line integral around this segment, also following the right-hand rule, by the way. I want to follow the right-hand rule. In this case, C goes this way, so the positive surface is that direction, okay? So if I look at the line integral di here, integral of f dl over loop ci, okay? Then of course this vanishes, right? In itself, if I take the loop to be small, but I can take the limit. And the limit, the area here is given by dA, the magnitude dAi, right? And dAi pointing in that direction. A lot of this is from Math 53. dAi of 1 over dAi, just the magnitude, and it's an integral of FCI dl, right? This limit exists. And it's defined as a curl of f, right? Projected in the direction of, it's defined to be in the direction of perpendicular to the TA, okay? Okay? Then then I can recalculate this integral I, right? And this integral I becomes a sum over all the small little partition, I from 1 to n, right, of dAI, okay, times 1 over dAI of the integral over Ci f. Okay.
Hi, how you doing, sir?
Oh, yes.
You in class?
Well,
I think you're recording today.
No, I'm not. I actually requested something. I will apply to this,
Okay. The
screen cache, right? But I'm not ready for it.
Are you not ready for it?
I even you there, so you can,
Okay.
I'm not doing it today.
Okay.
Because you guys just check
Yeah.
because
Yeah, we
there was nothing happened, right?
Okay.
Yes, sorry, but I did email her back. Yeah.
Okay. Thank you.
Okay. Thank you. Anyway, is this clear so far? So this integral is just a sum over all the little patch here, okay, of this little differential line integral, right? And the reason that you can do that is because the contribution, suppose I look at this boundary, the contribution coming from a line integral going that way cancel the contribution of the line integral going this way.
So kind of like when you're doing circuits.
Yes.
Is that related at all? When you do the like amperes?
No, nothing. This is just
Okay.
mathematics, right?
Yeah.
And this then becomes in the limit when dA goes to dAI, or dAI goes to 0, right? Then this is just this integral of dAI of curl, which is dot product here, curl of f, right? At I. Okay. And then here, let me just take one more step. This is still sum over I. Okay. Then that integral becomes curl of f times t. Okay. And curl of f is a direction, and the direction is always normal to the surface that you can see. Okay. Or in this case, it's just the dot product. So once you have that, then this is then we have Stokes theorems, right? Because this integral is just the line integral. It's integral of curl of f dA over surface S is equal to a line integral of f c. So I can convert a line integral over the perimeter as a surface integral of this quantity called curl of f. Okay. And in Cartesian coordinate, curl of f is can be written as this, right? And this is given as a determinant of the following. And if you're not familiar with the definition of a determinant, you should review it in your math book or in Purcell. I mean, I can write this out, but take a lot more time to do that. Is this familiar to you? Somehow? This you can write it out. That this is actually a product of this is a vector, by the way. This is a vector that has component in the x, y, and z, right? And it's given by this. Okay. Questions so far? No question?
I mean, why is the determinant is? I mean, why is it equal? Like, how do you?
Oh.
Where did I mean?
Yeah, here I'm skipping steps, right? Why is this written this way?
Yeah.
Please review it in myself.
Okay.
We have a very physical discussion in chapter 2, right? I haven't looked at any vector calculus book in a long time, but I'm sure that people need derivation in a vector calculus book, in a math book.
Okay.
But Purcell tend to be very physical. So, at least I was talking to either Charlie or Meiji at some point that it seems to be like the discussion of curl in Purcell,
okay.
because it's really good.
Okay.
Right? It at least gives you an understanding what curl is. Right? It's very physical. Right? So we do the deformity of a field. But I don't have time to write it here. So this is as much as I'm going to say that the curl is defined by this quantity here, and then the Stokes theorem says that the surface integral of a curl of a function of a field, right, is equal to a line integral of the boundary. Right? Again, it has to satisfy the right-hand rule, right? You define the boundary, so it goes along this way, right? So the surface, all the elements, dA, right? dA is positive. The normal of dA points along that boundary. Okay. Questions so forth? So, now once you have this machinery, then you don't have to express things in the integral form. In particular, say electrostatic, right? You have a line integral of dl is equal to 0. Okay. Then this tells you that a curl of E over a surface dA is equal to line integral of dl. Is equal to 0. It's always equal to 0, no matter what you choose as your loop, no matter what you choose as your surface. Therefore, the curl of E is identically 0 in electrostatic, right? And then the other equation for electrostatic is that this is from Gauss law, the divergence of E is equal to rho over epsilon naught. This is all there is to electrostatic. You're familiar with this equation. Now you know the other differential form of the equation. Okay? How about in magnetostatic? In magnetostatic, you already know one, right? The divergence of E is equal to 0, right? Because this is just the Gauss law for magnetic field, right? There is no magnetic monopole, there is no charge, there is no magnetic charge, therefore the divergence is 0, right? This is an analog in electrostatic, right? But the other one is of course the Ampere's law, right? The line integral of dl over a loop C has to be given by mu naught integral of J dA. Right? But the left-hand side, by Stokes theorems, right? By Stokes theorems, the left-hand side is just a surface integral of a curl of E dotted to dA, right? And is equal to mu naught J dA. And this is true for this is a general law, right? It's Ampere's law. So it's true for any surface, any boundary curve, okay? That satisfy, of course, the right-hand rule, okay? Right-hand rule is very important in magnetism. So then the integral has to be the same. Therefore, the curl of B has to be equal to mu naught J. Right? This is the equation for magnetostatic, the two equation. Okay? Questions so far?
Is that have to be a closed curve?
Say it again.
Does that have to be a closed curve?
Here, yes, this
Or
will be
a
a
closed
closed curve.
surface?
Closed loop. This is a closed loop.
Yeah.
No, did I make a mistake somewhere? This is a surface. Right? This is the closed curve.
Oh yeah.
Right? So if I take a closed loop like this, right, and I calculated the line integral of B along that surface, it has to be equal to mu naught times the current enclosed, right? And I can re-express the line integral as a surface integral of the curl of B. right? But this is a general, this can be any
Okay.
surface
Okay.
and any curve that bound the surface, right? Therefore, the integral has to be the same.
Yeah.
The curl of B is mu naught J. Okay? So those are the two equations for magnetostatic. And maybe I should erase this. Maybe I'll use it later, but I have to erase it. So again, let's see, what's the motivation here? Earlier I mentioned that we want to look at the field coming from a loop, a dipole, finite solenoid. So let's see where we are on that. Now in electrostatic, you know because of these two equations, then you can express electric field as a gradient of potential, right? Okay, and then you have a solution of a Laplace equation. Let's go over that now. This is electrostatic, right? So I'm wondering, then if you do the same thing, this is so powerful that it basically can solve anything, right? Because from this, if I have any finite charge distribution, right, say rho is 0 at infinity, okay, then you can find a potential. You just give it by 1 over 4 pi epsilon naught, an integral of rho over r, right? Oh, this is used and you have to be careful with the notation here, but this is the idea, right? The potential is 1 over r, and you sum over the charge distribution, right? And then once you know what the potential is, then you take the gradient, you find the electric field, right? We want to have the same program for magnetostatic, right? Is there such thing as VM? Okay, and it turns out there isn't. Well, there it's not a scalar. And the reason is this integral dl is not equal to 0. It's not identically 0, right? The line integral of B around a loop is not 0, or equivalently, the curl of B is not 0, right? Therefore, I cannot express B as a gradient of some. I cannot have a state function because B is not inserted here. Okay? So if I take this concept Vm to be an integral of B L from some reference R naught to R, right? This is path dependent. Okay. But turns out you can do more than that. Before I do that, there is a little bit of factor identity that you need to know. And this will make things easier. Right? This is also from math 53 or 54, right? For any field, for any vector field or any scalar field, then the curl of a gradient of a vector field is always equal to 0. This is an identity. Right? And also, if I have any vector field f, then the divergence of a curl of f is always equal to 0 also. Identity. Okay?
Is this little f a function or?
This is a scalar field.
Scalar field.
Any scalar field, well-defined scalar field, goes to 0 at infinity, or this is a vector field. You probably recall this from math 53, you know. If not, you can always do the math. It's long pages of, not pages, 1 page of algebra. Let's do it. since we cannot use a scalar field because the curl of B is non-zero, maybe we can use the other equation, right? Because the divergence of B is equal to 0, right? It's always equal to 0. There is no magnetic monopole, right? If there is a magnetic monopole, then things will be slightly different. You can still discuss this, but it's beyond the scope of the course. Just want to make sure I don't skip step. Then, if you look at the second identity, right, the divergence of a curl is equal to 0. Maybe we can actually write B as a curl of something, right? Let's call it something A, right? Then if you take the divergence of this curl, it's always identically 0. Okay, and this is called a vector potential. Right? I haven't shown that yet, but this is possible. And it turns out it is possible, right? Let me do one more thing before I continue. Let me just continue. So if this is possible, then I can insert this into Ampere's law, right? What does Ampere's law says? It says that the curl of B, right now I'm going to switch to a differential notation, right, is equal to mu naught J, right? Then curl of A, right, is equal to mu naught J. Okay? There's more stuff I need to use this. Sorry for all this vector identity, guys. Another vector identity. This is the last one I found. This identity. It's not that I remember how to derive them. I do a lot of algebra. And so if I have a curl of a vector field, after pages of algebra, we get that this is equal to minus the Laplacians of f, but f here is a vector, okay, plus the gradient of the divergence. Okay? So this is just to write it out so that, because you're not familiar with the Laplacians of a vector, right? This is just it's just a vector with 3 components. This is just the Laplacians of fx plus dtx of the divergence of f. Divergence of f is always a scalar, right? Right? Okay? And this is already the x direction, right? And then Laplacians of fy plus dty curl of f in the y direction.
I'm kind of confused. Isn't the gradient of the divergence what the Laplacian is?
Gradient of
Or
wait, say
like,
again?
wouldn't you just get minus del squared f plus del squared f equals 0 from that equation?
No, this is any vector field. Any. This is just vector identity.
Uh-huh.
Right? Nothing to do with vector potential or magnetic field, right?
No, I just mean because like the right term is like del
No.
times del
No.
dot.
Good point, right? A Laplacian is actually a divergence of the gradient.
Oh.
Right? This is flipped, right? So curl of a curl is a Laplace minus a Laplacians plus the gradient of the divergence. Right? It's not the same thing. Laplacian is a divergence of a gradient. So it gives you a scalar. This gives you a vector. This is a vector.
Oh.
Right? Well, yeah, this is a vector, and this is also a vector because of that, right? So let me just complete all the term, the Laplacian of Fy plus dd z divergence of F in the C direction. Right? So that's that term, right? So knowing this, now we can evaluate the Ampere's law. Curl times curl of A is equal to mu naught J, right?
Is it a negative on each of the Laplacian?
Oh, yes, yes. It's negative. Sorry
So-
about that. I make more mistake. It's easier to see from here.
Yeah, that's a FZ.
Yes,
Wait, so in this case, how is it that you're adding the left side, which is a scalar, and the right side, which is a vector?
No, not. So here, this is a vector, right?
Uh-huh.
So this has component dt. In the x direction is the gradient with respect to x of a divergence. Right?
Oh,
Here, this is the fx component of the Laplacians of the fx. Right? And then this is the x component, y component, and z component. This gives me a vector again. I'm just writing it out term by term.
uh-huh. Okay.
Okay? Okay? Is this clear? This is probably one of the most algebraic. It's actually pretty interesting if you go through it in math 4. Less so when you only do it for 20 minutes in a lecture. So this becomes minus the Laplacians of A plus the gradient of the divergence of A is equal to mu naught J, right? Okay? So you're getting there. I mean, electrostatic gives you Laplacian of V is minus rho over epsilon naught, right? Except for this term that we don't like, extra, right? Nuisance. Say, right? Then suppose let's pretend this is 0. You know, I'll show it 0. If it's 0, then what you have is a Laplacians of A, right? Laplacian of a vector potential A is equal to minus mu naught J. Okay? And then you have some mathematics, a piece of mathematics that's exactly the same as the Laplacian electrostatic, except that you have 3 terms, right? Yeah. I can write it out. This is basically the Laplacian of Ax is equal to minus mu naught Jx, and so on. Right? There are 3 equations here. Okay, for each term. But each term is actually exactly the same as a Laplacian for electrostatic. Okay? Good. Except that we have to take that down, right? Any questions so far?
Are you just supposing there's some A that equals to B? Like
Yes.
a curl with some A?
So it's possible to choose an A. We have a choice, right? Is that what you think?
Yeah.
Yeah. You have a choice, just like in electrostatic. I mean, in electrostatic things are a lot simpler, right? In electrostatics, because you always want to think about electrostatic. In electrostatics, I can change V plus a constant, right? So it's also called primes, right? Then the electric field, which is minus a gradient of V, right? Goes to minus the gradient of V plus constant. It's still equal to minus gradient,
Oh, I see.
right? So for electrostatic, I can shift the potential by a constant. It doesn't affect the electric field, right? So let's see if something similar is happening with vector potential. Vector potential things are more complicated. For one, it's a vector, right? But what's the V, the quantity of interest, so the quantity that's real, that means that we think is real, is a magnetic field, right? And it's written as a gradient of a potential, right? It's not quite clear yet what this means and whether this is actually a physical, experimental quantity that you can measure or not, right? For now, it's mathematical, right? But in the end, this is what you know, right? But so if I change A to A plus some gradient of some scalar, since the curl, where is that? It's gone. There is a vector identity. I know this is a lot of stuff, but the curl of a gradient is always zero identity, right? Okay. Then if I take the curl, let's call this A prime, the curl of A prime, then it becomes the curl of A plus the curl of a gradient of chi, right? But this is identically zero, right? And this is equal to the magnetic field. So I can make this transformation. It's called a Gibbs transformation, if you like a fancy word. Well, actually, it's me. But there is for now you don't have to worry about it. There is a transformation here, replacing A with a gradient of something, right? And then you get the same. Okay? So there is some freedom that you have here. Okay, and I think I'm running out of time, but because of that, and I won't show this, you can look at it in final lecture or something. It's not in yourself. I did. By the way, do you guys read the final lecture volume 2? It has another page on electrostatic that's also interesting. Okay. But because of that choice, right, I can always choose if the divergence of A is not zero, right? I can always choose another A prime given by A plus the gradient of chi, right? And as long as everything is well behaved, goes to zero at infinity, right? Then this is always possible. It's always possible to choose an A prime in such a way that the gradient of A prime is equal to zero. Right? Obviously, it is called a case choice. This is a case choice. So, well, I call it A prime, but basically choose a vector potential that the divergence is equal to zero, then everything becomes simple. What you have then is just this thing goes away, right? So you're left with the minus the Laplacian of A is equal to mu naught. Let's put the minus sign on the other side, minus mu naught J. Then this has a solution we already know. As long as J is finite in extension, right, it goes to zero at infinity, then the solution is given by, I'm just copying now, right? I don't remember anymore, I'm just copying from that. I'm copying this equation, right? Then the vector potential A will become mu naught over 4 pi. The 4 pi I pull out from the analog of this equation, okay? Because suddenly there is no 4 pi here, but 4 pi appear over here, right? So it's the same thing here. Mu naught over 4 pi, okay? The integral of J at r prime, p prime, v here is volume, okay? Divided by r minus r prime. This is distance. Knowing the current distribution, I can calculate the vector potential, right? Just like in electrostatic, knowing the charge density allow me to calculate the potential, right? And then knowing the vector potential, you can always calculate B. It's just take the curl. Just take the curl, you're done. Right? So now we know how to connect, in general, between current density to magnetic field. Right? Knowing the current density, calculate the vector potential. From the vector potential, calculate the magnetic field. And then you're done. Okay? So with that in mind, let's see, I want to leave 5 minutes for all the demo. We did that part. Any question on this? I know this is kind of dense, maybe, right? Not dense, but it's introducing new concept. Vector potential is very powerful, very useful. It's used all the time when you study physics. When you look into photons, right? When you look into concept of photons, this actually coming from vector potential. This you will learn later on.
Do you think that maybe you could go over it again, like your reasoning? Because you said that, you would think that there's an A because the divergence of B is 0.
Yes,
but,
yes.
So like, what's the connection exactly?
Oh, because there's a vector identity, right? There's 3 vector identities. The most complicated one here, right? But there is another 2. The arrow is always true, right? If you don't remember anything from vector calculus, remember this. The fact that the divergence of a curl is 0, and the fact that there is no magnetic monopole that gives you divergence of B field is equal to 0. So maybe B field can be written as a curl of some vector. In this case, I call it, it's called A, the vector potential, right? And I just showed you that it actually can, right? Let's see, what else? Yes, just to give you an example, because I don't want to make things too abstract, let's just talk about one example before I do the demos. I thought there was 2 examples. There's only 1 example, maybe. Yeah, for melodies. Take a solenoid again. Yeah, I'm drawing it rather nearly, but make sure that the direction is correct, right? With the right rule, there's an I naught, there's a winding number of N. We know there's a P field inside. Inside is given by mu naught and I, right? And 0 outside, right? And the question is, find the vector potential everywhere. I'm working backward in this case, right? Because we're familiar from Ampere's law in symmetry, we know how to calculate magnetic field, right? So say from magnetic field, from knowing the magnetic field of a solenoid, how do we find the vector potential? And this we can do, right? And because B is a curl of A, right? So if I take a surface integral of a curl of A over the surface, this has to be equal to also the same thing, right? I'm doing the same, I'm not doing anything different now. Right? But the left-hand side, by Stokes' theorem, right, the left-hand side is given by surface integral to a line integral. Right? Has to be equal to a B. Right? So in particular, the solenoid, let me redraw the solenoid, let me redraw it as just a cylinder. Okay, so there's current along the perimeter of the cylinder, right? This is the center here. So let me consider a loop C with radius R, right? Finding A inside. R less than, which has the radius A, say, or R naught. R less than R naught, right? Then first notice that A cannot be in the C direction by symmetry, right? And A cannot be radial. Because why? We chose a gauge already for magnetostatic. We chose a gauge that the vector potential is the divergence of the vector potential is 0, right? But so in this case, if there is a radial component, right, then it will be radial everywhere, right? So it will have a divergence, right? The Gauss law will not be 0, right? So the only possibility is that A has to be tangential, right? So the line integral of ADL here then becomes A tangential by symmetry. You can pull it out of the integral, and this is you're familiar with this from if you study of electrostatics times 2 pi r, right? And the whole thing becomes equal to B, the flux of B to this surface, right? But B is constant. Let me just call that B naught, right? Times pi r squared. The pi cancel, so A free, right? Component of A in the tangential direction is B r. Okay. And you can do the same thing outside. This discussion should be similar to remind you of things in electrostatic, right? Outside, then if I look at A, R bigger than R naught, right? Then again, A phi times 2 pi r has to be equal to the flux of B through A, right? But the B field is 0 outside. There's only one 0 inside, right? So this is just B naught by R naught squared, right? So A phi here becomes a pi cancel, B naught R naught squared over 2 R, right? I draw it, R naught, A, it goes linear like that, this one is in the tangential direction. This is a vector of a solenoid, right? Close to the center of a solenoid, say around here, say. So that we can consider this to be infinite. Any questions so far? So this is working backward, of course, and it's kind of useless, but it gives you an idea what the vector potential looks like. Useless in the sense that it will not, you already know what P is, right? What introduce P. I just want to give you the character of the vector potential, because later on is what vector potential is what will give you the magnetic field. So with that in mind, let's do a magnetic field. So this is a magnetic field coming from a line of wire. Shows? Oh no, this is not. See, this shows I'm so bad. Go home. Can you see the pattern?
Yeah.
This is the magnetic dipole here from iron. It's an iron field. You guys have seen this before, right?